All right, well, we have our test coming up in our next lesson, test over chapter number 16, our calculus chapter. Let's review some things we talked about over the last, well, I guess several weeks now because of senior trip, kind of taking a week of this away. But let's review. We started by talking about this idea of not necessarily, well, we started actually with function notation, right? For instance, like f of x equals, 4x cubed negative 7x plus 5. And if I said, for instance, what is f of 2? Well, class, you would plug in a 2. And what would we get here if you plugged in a 2?
25.
Close. Unless I'm wrong.
23.
I have 23. So I had 4 times 8 is 32 minus 14 plus 5. I did this first to get the 37 minus 14, and that's where I was getting the 23. What if we said f of m cubed? What would that be? Jamie?
We would have m cubes everywhere.
So,
For m cubes cubed,
which would be
9,
m to the 9, because when we raise the power to a power, multiply the exponent.
minus 7 m cubed, and then plus 5.
There we go. What if we had f of, let's say x plus z? Ugh. Now what would we have to do, Quentin?
You have
To cube that binomial, wouldn't we? Yeah, then the whole 1, 3, 3, 1, x cubed, x squared, x to the first, z gone, z to the first, z squared, z cubed. We have to distribute 4 to all of that. So this would become 4, 12, 12, 4, all signs positive, right? And then we'd have to plug that in here also to get
negative 7z minus 7. Or negative 7x minus 7z.
yeah, negative 7x, negative 7z, and then of course we'd have this plus 5 at the end and no like terms, so we just leave that big ugly answer, right? But that's function notation. And then I went from there and said, well, what if I didn't want to actually take, for instance, f of 2? What if for some reason I couldn't take f of 2? It wouldn't work out because of some issue. Well, I could find, for instance, f of 0, f of 1, f of 1.5, f of 1.9, 1.99. I could approach the 2. What was that idea called? Kind of used it all throughout this chapter.
The limit?
The limit concept, where we would say, okay, well, let's take the limit as x approaches 2 for a 4x cubed negative 7x positive 5. But I said, unless there's a reason to use the limit, let's just plug it in. And here, there is no reason not to just plug in the 2, correct? So, let's plug in the 2. And sure enough, we do get 23 again. There would be an issue with this, though. For instance, if we had the limit as x approaches 2. If we had, for instance, a denominator of x minus 2, right? Because there you can't plug in the 2. So let's say the numerator was something like, I don't know, x squared, say positive 3x negative 10 or something like that. Well, let's say it was something like that. Then what would we need to do in this case? I mean, we could do the 1, 1.5, 1.9, 2.1, go on the other side of the 2, right? But there's a better way. What was the better way for a limit when you couldn't just plug in the number?
Synthetic division?
We could use synthetic division, remember, where in the half box we would put
2.
the actual limit value, which is always the inverse here, right, the positive 2. And next to it we would write
1, 3, negative 3.
there we go, and we would bring down the first term, which is a 1 in this case, and we'd multiply,
2.
and we'd add,
5.
and we'd multiply,
10.
and we'd add,
0.
and we'd put 1 power less than this, and then descend it, which means it's gone, and really this would just become the limit of x plus 5, as x approaches 2, which would just equal 7. There was another way, though, Quentin. Do you remember the other option besides synthetic division? That was often available to us, not always, but often. Remember we said we could try to factor the numerator. into an x negative 2 to cancel, and then here, x and x gives x squared. Signs have to be different, so we need a negative and a positive. Negative 10, we need a 2 and 5. And then the x plus 2's could cancel, and it would still give us the x plus 5. So synthetic division, if it didn't look like it, would factor and cancel. And factoring and canceling, of course, another easy way to work with that. Questions on these? Questions on these? Do you want additional practice with limits, functions, anything like that?
Maybe one that, like that one.
Like that one? Yeah, absolutely. All right, so let's... take the limit as j approaches, let's see, how old are you?
Almost 19.
Almost 19, so you're approaching 19. The limit as j approaches 19. Now this is unfortunate because that means we have to have a j negative 19 to the bottom. And that also is unfortunate because that means I have to think of something here. Oh boy. All right, let's see what we got here. We got a j cubed negative 18 j squared.
We could say something like, my birth month is 5.
Oh no, can't do that. Couldn't possibly do that, Jane.
Outside.
Negative 24j, positive 95. We're definitely doing synthetic division here, right, folks? Yeah, I shouldn't have asked for an age. That was a bad idea. Should have said pick a number 1 through 6.
Do we keep the signs in,
When you write the things next to, yes, the sign is, because the sign is part of the number. All right, so we divided by synthetic division, and that became the limit as j approaches 19 for what, Jamie?
wait, you mean what it becomes?
When you
after?
divided it, yeah, what would you get for your answer? The initial answer.
I have a 19 j squared plus j minus 5.
J squared plus J minus 5.
Should have been just a j squared plus
Oh, I see what I did
j
wrong.
minus 5.
Yeah. Besides, I put the 19 there instead of 1, but I did everything else right.
I got you, okay. So then, Jamie, we need to evaluate now. We couldn't evaluate before because we couldn't plug in the 19. Now we can. What's 19 squared?
361,
Plus another 19, and then we minus the
Okay.
5, and we get
375.
375 as our answer. Quite good to go. Do we need another less annoying one, or we feel good to go on limits and functions?
I'm fine.
All right. From there, we talked about the slope of a curve. Now, we said the slope of a line is easy, right? Slope of a line class is defined as 1 over what? Rise over 1. But a curve doesn't have a slope per se. It has lots of different varied slopes. So we said for a curve, we would have to find the slope at each individual point or at any given point by finding the slope of a tangent line. And we had a formula we would use to find the slope of a tangent line, and it used a limit. The limit as, remember, slope is change in y over change in x. We said the change in x would have to approach 0 to get an accurate slope of the tangent. What was the rest of the formula? The slope of the tangent is the limit as delta x approaches 0 for
F of delta x minus
Yeah, so make sure you have that memorized. I told you you're going to need to know that for quizzes and tests, and of course this is a test coming up. Make sure you have the slope of a tangent formula memorized. Not that we have to use it though, because we have a shorter way of doing all this. What term refers to the slope of a tangent line? Or refers to, for instance, the function we could use to find the slope of a tangent line, maybe. The first derivative. The first derivative refers to the equation, in a sense, or the formula we would use, the function we would use to find the slope of a tangent line. And of course, we have a shortcut, obviously, finding the slope of a tangent. So if we had some obnoxious function of x, like for instance, I don't know, j cubed minus 18j plus 24, or j squared, plus 24j minus 95. If I wanted to find, I don't even remember if that was exactly what we had last time, but if I wanted to find the first derivative, what would I do? Jamie?
You went down with the exponent. I can't remember. Oh, you multiply the like 1 times 3 to get 3. Then you had j1, and it was 18 times 2, so 36. And then it was just constant.
24, because this becomes a j to the 0, which of course means it's a 1, which times 24 is just 24, and the constant would fall off, right? If I wanted to take a second derivative, Quentin.
It would be 6j minus 36.
Good, 6j negative 36, and so on and so forth. Remember we said whatever the highest power is, that's how many derivatives you could take. Well, what if I wanted to know the slope of the tangent line when x equals 4? What would I need to do?
Plug in 4.
Where?
For j. Well,
Oh, sorry, with j equals 4. That should be f of j, not f of x. We want to be accurate about it. Slope of the tangent when j equals 4.
plug 4 in the original equation.
That would give me the y value, or the f of x, or f of j value, right? But if I want the slope, I've got to plug it in the first derivative, don't I? So I would say the slope when j is 4 means f prime of 4, which, this is probably going to be rather awful, but 4 squared
6
times 3,
48.
48 and 24,
72.
72. All right, what about 4 times a negative 36?
Negative 144.
Negative 144 plus a positive 72?
96. Negative 96.
Negative 72. Because it's half of, right? So negative 144, positive 72 taken half, so negative 72 would be the slope when j is 4. All right, so let's take a slightly more normal looking function, and one that's not quite so obscene. Let's take f of q. Normal looking? Anyway, let's take f of q is equal to a 4q squared plus 5q negative 8. And I want to find the slope of the tangent. I would say when q is 19, because q is 19 now. Just turned 19 a couple days ago. But we're not going to go there because we did that already. We didn't like that path. So, I don't know. You've been here for a lot of years. What was your favorite year here? Was this your favorite year being a senior? We'll say when Q is 12. That's still an easier number to work with. And you have a calculator. And Jamie's like, 7th grade, Quentin, 7th grade. It's the best 5 years of your life. I'm kidding. He wasn't in 7th grade for 5 years. I'm just picking on it. People always ask my dad, so what did you think of college? Like, did you like college? Like that freshman year, was it bad? He's like, no, freshman was the best 7 years of my life. Darn freshman speech. I'm not gonna lie, I was scared of freshman speech. I survived it. All right. If I want the slope of the tangent, class, I've got to have the first derivative. So I need a prime of q. Q.
8q plus 5.
And so I'm going to evaluate, Jamie,
You plug in the 12 for the cube.
f prime of 12, which gives us
It'll be 96 plus 5, which is 101.
101. That's some really steep slope. You almost got 100. You went above and beyond 100. This has been a fantastic year. Above and beyond perfect. All right. The numbers don't lie, Quentin. I'm just saying. You just can't argue with facts. All right. Questions on how to find slopes? I feel like we're good there. Now, we did talk about some specific functions, talking about movement of an object, and we said that distance directly depends upon time, remember. The longer an object moves, the further it gets, regardless of its speed. Okay? It may not get very far because it's moving so slow, but it will still get further if given more time. All things move further if given more time. So d of t could be a way in which we could describe the distance or displacement of a moving object. So if we had this function, for instance, and I wanted to find how far does an object move in, say, 7 seconds, well, I would just find d of 7. And how far does this object move in 7 seconds? Class.
120.
That's what I was getting as well. It's taking me a minute to get there. 120. Now that's distance, right? And we would say in physics, right? This is kind of a physicsy concept. Displacement should be measured in meters. So we'd say it moved 120 meters in those 7 seconds. Now we said if we wanted to find out how fast it was going, well, it took 7 seconds to go 120 meters, right? Except technically, d of 0, before it even started moving, how far had it gone? 1 meter, right? So it technically started 1 meter ahead of the starting position anyway, cheats, okay? And so, so really how far did it go in 7 seconds? What was the change in displacement? 119 meters, and that took place in a change in time of 7 seconds. So we could say that the average velocity would be, what? Divide that out on your calculator because I can't do that in my head. Yes, I can.
17.
Wow, that actually worked out even. That worked out great. I just made that up off the top of my head too. You're a witness. It has happened that a problem worked out great, just made up on the fly. 17 meters per second, that's average velocity, right? But that doesn't mean it was going 17 meters per second the whole time, right? Probably it's been getting faster and faster as time has gone on. If I want to know how fast it's going at any particular moment, I would need to use what we call the instantaneous velocity. But to find instantaneous velocity, I'd have to shrink this change in time approaching 0. We would have to use a limit. We would have to use a first derivative. And remember we said that instantaneous velocity is the first derivative, or d prime, of t. So if I want to know, let's say for instance, right at the 3-second mark, Quentin's like, I want to be greedy and say 1 second mark, but I know he's not going to let me do that. So right at the 3-second mark, well then first I'd have to find the d prime of t. And what is d prime of t, Jamie?
It'll be 3t, wait, no, 6t minus 4.
There we go, 6t minus 4. And so we'd find specifically d prime of 3, and how fast is it going right at the 3-second mark, Quentin?
14.
Only 14 meters per second, okay? So it's not even up to the average speed yet, right? In fact, if we wanted to track it, we could say, well, how fast was it going right as the start happened, class?
-4.
It was actually going backwards at then 4 meters per second, and then at 1 second, it had reversed course and was going forward at 2 meters per second. Then at 2 seconds, 8 meters per second. So you can kind of see the improvement, right? It's increasing in its speed every second, right? So we see the instantaneous velocity. In fact, by the time we get to 7 seconds, again, the average velocity may be 17, but how fast is it really moving at the 7-second mark?
30.
I mean, this is highway speeds, okay? So 38 meters per second. In fact, it's, I think, probably speeding on the highway, if I'm not mistaken. Probably closer to like 75 to 80 miles per hour. That's just a rough guesstimate in my head. All right, so yeah, it was starting by going backwards. Maybe it's rolling down a hill or something, and then it's able to start speeding up. It gets on that acceleration ramp where we accelerate so that when we get to traffic, we're going the speed the traffic around us is going, right? Like they talk about in driver's ed.
Hopefully. I ain't take
Jamie has this blank look on her face like she's like, I don't know what he's talking about.
Yeah,
I ain't take driver's ed. I'm in Alabama. So.
I haven't taken either. And
I think your
saw
insurance rates are cheaper if you do driver's
Yeah,
ed,
they
though.
are.
So it's worth it to pay the money up front for driver's ed. It's cheaper insurance rates. But anyway, I digress. But it's getting faster and faster and faster, which means it's accelerating. Now, I could say that it was going negative 4 meters per second when we started. Now it's going 38. What is the change in its velocity?
42.
42 is the change in velocity, but it's taken 7 seconds for that change. So we would say that the average acceleration class is 6 meters per second squared, right? But there's another way we could find, for instance, acceleration, because this is average acceleration. But what if I want to know at a moment in time what the acceleration is? I would need to know the instantaneous acceleration. And that comes from the second derivative. Well, we said the first derivative is right here. How would I find the second derivative d double prime of t?
6.
You just do it. And notice, this means no matter what time you plug in, it's always going to be 6. The average acceleration is steady. There is no varying in the acceleration. This is foot on the gas pedal with the same pressure without taking it off. Even when you're already going faster than the cars around you, that gas pedal just stays where it is. And until the blue lights come on and then sad things happen, right? Obviously, if we had a higher power function to start with, we would end up with a variable acceleration. We'd have to plug in, okay, at whatever time. For instance, at the 4-second mark. Well, there's nowhere to plug it in, so it's still just 6 meters per second squared at the 4-second mark, because the whole time it's 6 meters per second squared. Questions on instantaneous velocity, instantaneous acceleration? Do we want to work another problem or two like this, or we feel good about it?
I'm fine.
Okay? Obviously, if you're watching on YouTube and you don't feel fine, reach out, get some help there. From there, we talked about graphing with derivatives. And we said derivatives can be helpful because when you graph something, we really want to know where does the graph change direction, right? Wherever a graph changes direction, we have what we call a critical point. That's where the graph, if it was going up, starts going down. If it was going down, it starts going up. And down and up and down. We could have lots of critical points potentially, couldn't we? But wherever we have a critical point, we know that the slope of the tangent line must be 0. So we said we can find critical points by determining where the, slope of the tangent equals 0. Well, what do we call slope of the tangent? First derivative. So critical points can be found by setting the first derivative equal to 0. And that's what we've been doing there. So for instance, let's take a function. Let's see, like for instance, f of x is equal to x cubed minus say 3x plus say 7. Okay, if we wanted to find critical points, well, I said critical points are anywhere the slope becomes 0. Now we said slope of tangent is, so what do I need to do? Find the first derivative, which is, Quentin?
3x squared minus 3
And then we need to set that first derivative class
equals 0.
equal to 0. Now we have a little equation that we could solve. What might we do to solve the equation, Jamie?
Take the negative 3 over as a positive 3. Divide both sides by 3. Then take the square root.
And we'll get x is equal to
1 and negative 1.
1 and negative 1. Now that's two different x values. So we get a critical point where x value is 1. We get a critical point where x value is negative 1. But that's not a point. Those are just abscissas. We still need ordinates, the y values, the f of x values. How do I get those?
Plug in 1 and negative 1
Into
the original.
f of x. Obviously, if you plug them in here, you're going to get 0, okay? Because the slope is 0 at those points. But we want the y value, so we're going to go here and find f of 1 and f of negative 1. What do we get for f of 1? 5. Jamie, what do we get for f of negative 1?
Wait, which equation are you plugging into?
The original. This is a first derivative, that's a slope. This gives me y values or f of x values.
9.
So those are my two critical points. 1, 5 is a critical point. Negative 1, 9 is a critical point. But there was another thing we wanted to analyze. We wanted to determine, are these critical points maximum or minimum points, right? So to determine how the slope is changing, maximum or minimum, we said we need to find the second derivative. And what is the second derivative here, Jamie?
It's going to be 6x.
6x. And so we could say, well, okay, at the 1 critical point, the slope is trending at a rate of class 6. Now that's positive. That means the slope going into the point is negative, and then coming out of the point, it's positive, and getting more and more positive at that point. That makes this point class a minimum point. But f double prime of negative 1, Quentin, negative 6. Well, that means the slope starts out going positively, goes to 0, and then goes down negatively. It trends negatively, which makes this a maximum point. So when we go to draw a quick sketch graph, we would find the point 1, 5, something like that. We'd find negative 1, 9, something like that. And it goes down from there, goes up from here. Apparently something like that is what our graph would look like. And we can get a quick sketch of a curve just by identifying critical points and the behavior at the critical points. Do we want another one like this, or do we feel good about it? You're fine? Okay, all right. Now, of course, if we had a linear function, would there be any critical points? No. So if we had a linear function, remember something like f of x equals 4x negative 2. Well, there's no critical points there, right? Your first derivative is a 4, which when you set that equal to 0, that's a lie, right? Well, what would we do to graph something like this if there aren't critical points?
Straight line.
Think back to y equals mx plus b. Start by plotting the y-intercept at negative 2. And then from there, track a slope of 4. Rise 1, 2, 3, 4, and run 1. And you just graph a straight line like that. Okay, questions on that? All right, do we want to do anything more with this, or do we feel good about it? Okay, all right, again, if you're watching on YouTube, you don't feel good about it. You could go back and rewatch the lessons on critical points. Again, it's only a few lessons to go in this playlist. Or, again, reach out to me and get some help. From there, we went to the opposite of the derivative. This is what we did right after seniorship. This is what we just took the quiz on in our last lesson. The opposite of a derivative is called the antiderivative, also known as the, not integer, that's a nice easy number, either positive or negative, but an integral. Some people use the words backwards. In fact, some of our textbooks, I'm ashamed to say it, have used the term integral when they mean integer, and it just fell off. Oh, Billy. It fell off again. Here, Jamie, you take it. Give it to Genesis. All right. Anyway, integral, that's what we're talking about, right? An integral is the opposite of a derivative, the antiderivative, if you will. What's the purpose of the antiderivative or the integral, class?
To find
Obviously, the derivative finds slope and changes, if you will. What does the integral find? We just had a quiz on it yesterday. Area under a curve, remember? And we showed on the graphing calculator finding that area that's shaded in under a curve. So the integral used there. And remember, we had this symbol for an integral. It was this stretched out, skinny looking S thing. And we would integrate a function, usually with respect to x. So for instance, if we had, I think we had this a second ago, it was like an x cubed minus a 3x plus 4, or something like that. I think it was our function a minute ago. Well, if I wanted to integrate the function, instead of multiply to get a 3, and then drop it to an x squared, and multiply to get a negative 3, drop it to an x gone, like we would get for a derivative, we would do the opposite process. To get capital F of x, we would
Move that.
Divide and well, lower and then divide.
raise it up to an x to the 4th, and then we would divide the 1 by the new exponent to get a 4th x to the 4th. And so right here we get
Negative 3 halves x squared plus 4x plus c.
and then we tack on a plus c to recognize the existence of the constant, remember. All right, it's a little troubling that we seem to have forgotten this already. Shaking off the dust off the brains a little bit here. We remember this now? And we said this is what we call an indefinite integral. Often we would leave it this way. If I gave you more information, said, well, just want to let you know that f of 2 is equal to negative 7. Well, if you had extra information like this, you could actually calculate the c value. Remember, we would go ahead and evaluate.
Plug in 2 for x and set it equal to negative 7.
Yeah, we actually evaluate f of 2, and whatever we got, we set equal to the negative 7. So here we plug in a 2. 16 would take a 4th of that.
4.
We'd square the 2,
4.
but take negative 3 halves of that.
Negative 12. Well, negative 6.
Negative 6 when it's all said and done. Negative 12 halves or negative 6. We'd multiply 2 times the 4. 8. Plus c, and we'd end up getting that c plus 6 is equal to negative 7. Therefore, c must equal
Negative 13.
negative 13. And so we could go through and instead of a plus c, we could put a negative 13, remember. But it's still an indefinite integral. You're not actually finding area because technically, when you integrate this way with open-ended boundaries, no limits, it's kind of technically negative infinity to infinity, really. And so the area under the curve would be infinite. You can't calculate it. It's undefined. But if you chose to limit this, and you said, okay, we're going to take this function, and we're going to evaluate from the negative 2 to the 4 how much area there is. Well, again, real quick sketch. Remember we said we had a 1, 5, and we had a negative 1, 9. Actually, that was, what was the last function I just had up there? Because I don't know if this was exactly right.
It was x cubed minus 3x plus 7.
Plus 7. Let me make sure I got it right then, okay? This would be a 7x. And then here, we don't really need the negative 13, we just do plus c. But if we wanted to evaluate this way, okay, well, we know the curve, again, is going to go down and up. Well, at negative 2, cut a straight line down, and then at 4, it's somewhere way over here. I mean, it goes really high up, right? And all this area, I mean, it's probably going to be a fair bit of positive area here, isn't there? What would I do if I wanted to find that area given lower and upper limits of negative 2 and 4?
First you would find capital F of x, and then you would plug in your 4 and your 2.
Right, we'd plug in the 4. We would subtract whatever we plug in when we got the negative 2. So, obviously the c falls away in both cases. So if we were to evaluate the 4, for the 4th and times a 4th,
64.
64. All right, 4 squared times negative 3 halves,
24.
negative 24, plus, of course, 7 times 4,
4. Okay, and 20.
plus c. Okay, and then we plug in the negative 2. Well, negative 2 to the 4th, and then take a 4th of that.
4.
Negative 2 squared,
4.
and then take negative 3 halves of that.
6.
And then negative 2 times 7.
Negative 14.
And of course, all the signs are going to change. So when we change all the signs, we've got a 64 that's positive, 28 is positive. Oh, and then we have a negative c that cancels with this. The 14 is positive, and the 6 is positive. We add all that together, and goodness gracious, we end up with
112.
112. All right, then we got some negative stuff we can add, a negative 24 and a negative 4. And that ends up giving us a total area,
84.
84 square units of area under the curve. All right, so this is what we've done very recently. Do we want to practice another one of these, or do we feel like we've got integrals as well?
Fine.
Any questions at all? That's pretty much the test. Any questions at all on the calculus chapter? Again, what do we call the antiderivative?
Integral.
Integral, okay. Y'all weren't able to answer it a minute ago, so I thought I'd follow up on that. All right, and you don't have to know the big limit summation thing for the integral. All right, yep, that's pretty much it for the test. All right, your only homework tonight is to be ready for the test. So if you need to go back and re-watch some video just to refresh your memory, maybe go back and look at old quizzes and refresh your memory there. Do what you need to do to be ready to go for this test. The test coming up in our next lesson, lesson 166. The next few lessons after that, lessons 167, lesson 168, lesson 169 will all be review lessons. A couple will be kind of short, and then lesson 170 will be the final exam. So we have 3 short reviews after the test, and then the exam, and then you are done with senior pre-calculus. And I'll never teach you math again, etc. All right, well, have a great rest of your day. And when the bell rings, you are dismissed.